AQA, A-level physics, simple harmonic systems. This bit of the specification. Now, lots of examples in nature and lots of man-made, no offense to women, man-made objects approximate to simple harmonic motion. The equations that we look at, we basically look at a model, which is a very simplified model, but it's a pretty good approximation to lots of things. You know, a butterfly flapping its wings, that's almost SHM. Sound, we think of the air molecules in the air vibrating with SHM. A pendulum bob in this grandfather clock, SHM. A guitar string, the sound in a saxophone, a baby bouncing up and down, the water molecule, bits of an engine, waves on the sea, water molecules as the wave passes by, a kid on a swing. These are all approximately SHM. And by using the model, we can do things like work out the forces acting, work out the accelerations, work out useful stuff. Now, the two systems that we need to know, we have the mass on a spring and we have the pendulum. Now, for a mass on a spring, T equals 2 pi root m over k. Yeah, to work out the period, T equals 2 pi root m. M is the mass of the system, K is the stiffness of the system. So a mass on a spring, it's the mass, K is the stiffness of the spring. For a pendulum, T equals 2 pi root L over G. L is the length of the pendulum, G, little g, is acceleration due to gravity, usually 9.8. So these are the two systems that we need to know, a mass on a spring and a pendulum, and using these two equations, be able to rearrange them as well. For instance, if I wanted to know K, then I would square both sides and then rearrange it for K, etc. So we haven't done anything about pendulums yet in my videos. You do actually need to be able to derive this equation, T equals 2 pi root L over G. So I've gone through the derivation here, considering the forces acting on the bob. There's a bit of a small angle approximation in there as well. You need to know it. It's a bit fiddly. I'm not going to go through it. Read the video, copy it down, learn it. Yeah. T equals 2 pi root L over G. I'm much more concerned with actually using this equation. So here's mass on a spring example. A mass of 300 grams oscillates freely on a spring of stiffness 200 newtons per meter. Calculate its natural frequency. What mass would have a natural frequency of that on that spring? Pause the video, have a go, 3, 2, 1, and there you go. And I said you've got T is 2 pi root m over k. Be able to rearrange it there, so I've rearranged it for m. Okay, and here's an example using the pendulum equation. Pen, paper, calculator, and the answers are... And that was a cat in the background, by the way. Jolly good. So, energy and SHM. What happens to the energy of the system? Now, if the system is undamped, damping means that we lose a little bit of energy, or a lot of energy sometimes, every cycle. And we lose energy because of friction. So we lose energy to the surroundings because of friction. If it's undamped, then that means that the total amount of energy of the system stays the same. So looking at this graph here, the total amount of energy of the system, of the pendulum swinging, of the mass bouncing up and down, the total amount of energy stays the same. But what happens is that the energy kind of sloshes backwards and forwards between potential energy and kinetic energy. Either the kinetic energy is a maximum or the potential energy is a maximum. It sloshes between them. Okay? Now, looking here, when the displacement, let's say it's a mass on a spring, when the displacement is a maximum, then the kinetic energy is 0. The potential energy is a maximum. Yes, a half k delta L squared. Yes, and the same on the other side. When it's in the middle, our mass on a spring or our pendulum, then the potential energy is a minimum or 0. And the kinetic energy is a maximum because that's when it's moving fastest. So the energy sloshes between potential energy and kinetic energy. Learn this diagram, important diagram. Now, most oscillations are damped. It might be light damping, it might be heavy damping, it might be what we call critical damping. But basically, these oscillations, if it's left alone, if it's a free oscillation, then what will happen is that the amplitude will get smaller and smaller. The period stays the same. If it's a mass on a spring, then T is 2 pi root m over k, and you will notice that in that equation it does not mention the amplitude, does it? Therefore, the period has nothing to do with the amplitude. So the period will stay the same, but as it loses energy every cycle due to friction, the amplitude will get smaller. If it's a free oscillation, if you get it oscillating and then leave it alone, there's a kid on a swing, give them a push and then don't touch them again, and the amplitude will get smaller and smaller. It'll actually go down exponentially, the amplitude, but the period stays the same.